Hello friends, very happy to see you back again. In my previous video, I had discussed about the LU decomposition techniques wherein a square matrix could be decomposed into a product of lower and an upper triangular matrix. Also discussed about certain limitations that the decomposition method showcases, which is not able to handle row exchanges when we are representing a matrix in the upper triangular form. So I have come out with this video which we shall take care of row exchanges using what is called a permutation matrix that we represent it as P here. So the decomposition method is called PA is equal to LU decomposition. Let us learn about it in this particular video. Also learn why is it better when compared to the LU decomposition, and learn to solve a few problems of decomposing a given matrix in this format, and also apply it to solve a system of equations. So this would be my focus in this particular video. So let us begin by defining what is this PA equal to LU decomposition in my next slide. So we are going to discuss about the decomposition of the type PA equal to LU, of which we are aware surely of what is A. A is a given matrix, L is a lower triangular matrix, U is an upper triangular matrix. So naturally the question would arise to know what is P. Now here this P is called a permutation matrix. We shall define it now. It is a square matrix of any order, say, or generally it is n by n order, which is obtained by rearranging the rows of the identity matrix. So if we take an identity matrix of order n, and if we do any rearrangement, then such a matrix that is obtained, which is called a permutation matrix. Now this is a matrix with a speciality that it has only one non-zero entry in each row and in each column. And what is that non-zero entry? It is always going to be 1. So this is the speciality of a permutation matrix. So I could call, if I say a 2 by 2 matrix, 1 0 0 1, that's one matrix that you could write, or you could write 0 1 1 0. So this is also one permutation matrix. If it is a 3 by 3, our general 1 0 0 0 1 0 0 0 1 is the general identity matrix, because you have every row. If you see, in every row you have only one non-zero entry, and every column you see there's only one non-zero entry, and that non-zero entry is just 1. So you could even rearrange them. That's what we mean by rearrangement, where you could interchange rows this way and then place it, that same particular condition would be satisfied. So in such cases, these matrices that we are called permutation matrices, and these are used because we are talking about row exchange that's going to happen in our matrix. So these were, whenever there's a row exchange that is happening, a permutation matrix is getting included in it, or it takes care of that row exchange. Let's see how in later, but as of now let's focus only on the definition and see a few examples as I stated here. So these are 2 by 2 matrices, and these are 3 by 3 permutation matrices. Now, some special properties of permutation matrix is it's a non-singular matrix, and the determinant is always plus or minus 1. And every permutation matrix P is an orthogonal matrix. So that means P inverse or P transpose is equal to 1. So we could say that P inverse or P transpose both are the same, and we can say both are equal to P itself. P inverse is equal to P transpose is equal to P. That's a very important property. And what happens is, if P is multiplied by a matrix from the left, so I told you that the permutation matrix takes care of the effect of interchanging the rows of A. So when you multiply a matrix A from the left by P, then that will take care of, PA will take care of the effect that happens when we interchange the rows. Whereas when we multiply P from the right, that is AP, if you do, then this will take care of the effect of interchanging the columns of A. So the way you multiply P, it talks about or it takes care of the effect of interchanging of rows or columns respectively. And then this is a new matrix. As I said, for a permutation matrix, the product PA is a new matrix whose rows consist of the rows of A rearranged in the new order. So when I want to multiply, when I have a matrix here and I would like to note down, it is I've given say A11, A12, A13, A21, A22, A23, A31, A32, A33. If this is my 3 by 3 matrix and I want to do the exchange of or the interchange of the second and the third rows, so that will give you here 1 0 0. I am interchanging the second and the third, so this will become 0 0 1, this will become 0 1 0. So when I multiply these two, I get first row is not touched, the second row, it becomes the third row is becoming now A31, A32, 33 will become the second row, and the second row now is becoming the third row. So this is taking care. Instead of interchanging here, this is A, you're multiplying it by P, and the interchange of the rows is taken care in the permutation matrix so that the product will automatically give us the resultant matrix. So that is the application of permutation matrix, which beautifully takes care of interchanging of any rows or columns by multiplying it on the left or right consecutively or subsequently. So I have shown it here where PA is equal to this. PA here is equal to, I have now interchanged which two rows? Here the second row, the second row is the 0, 1, 0, 1, 0, 0. That means I am performing the operation of interchange of R1 and R2. So what is happening? This is my original matrix A. This is my permutation matrix P. And so what is happening? The second row is occupying the first, second set of row elements are occupying the first row. First row elements are occupying the second row. So that's the resultant of PA. So a very beautiful kind of an application of permutation matrix which takes care of the interchange or the exchange of rows. Let us see in our next slide, how is this PA equal to LU decomposition better than the LU decomposition which we studied, and where is the difference that we can see. So let's do that in our next slide. Before I proceed with the algorithm of PA equal to LU decomposition, here is a slide which talks about how advantageous is PA equal to LU decomposition when compared to LU decomposition. So as we are aware, LU decomposition does not work for every matrix. Now I can give you an example here. Look at this matrix. It is 0, 1, 1, 0. So this cannot be decomposed in the form of a product of two matrices in this manner. A0, BC multiplied by XY 0Z. So it is an lower triangular multiplied by an upper triangular. You cannot factorize this particular matrix in this product in this form because of the existence of such inconsistencies that you get. Inconsistent equations, when you multiply them and equate them to corresponding values, you get equations which are unsolvable, and therefore it cannot be decomposed, and that's where you require row interchange in order to simplify it. And when you require row interchange, then PA equal to LU comes into the picture, or the existence or the application of permutation matrix comes into play. The LU decomposition works only if all the principal minors of a matrix are non-zero. So if we take up a matrix of this kind and we calculate the principal minors, 1 is 1, then we know how to calculate the principal minor 1, 1, 2, 2, and that gives us the value 0. So this has no LU decomposition. So these are the conditions where many matrices do not have LU decompositions. And especially when any diagonal element, suppose a diagonal element is 0, our process of Gaussian elimination says you divide by that pivot element. So since it involves division by 0, which is absurd, this will not take care, and this such matrices having 0 in along with the pivot will not be able to be taken care of in the LU decomposition method, and thus this permutation matrix again comes into help. The next one is PA equal to LU decomposition is faster then finding elementary matrices, inverting, multiplying them. So the concept of P helps us complete the computation in a better way. And the most important one is any matrix that has PA equal to LU decomposition. That is not just square matrices, unlike in the case of LU decomposition. So when I can do this decomposition for not only square but also for rectangular matrices. So in which case, our P, which is a permutation matrix, will be of order m by m, where if A is your matrix of order m by n, then the lower triangular and P, the permutation matrix, will have the same order, which will be the number of rows by number of columns, which is the same m by m. Number of rows and columns will be the same as m, whereas U will be of the same order as that of A. So when we multiply both sides, you will get the same ordered matrix. So if I say talk about m by m, see P here is P is an m by m matrix, and A, which you already know, is m by n matrix. And if the right hand side L is again m by m matrix and U is m by n matrix, so you will see that both sides that you get will be an m by n matrix. So when it is a rectangular matrix, when A is rectangular, please note here that P and L, which you are taking, are all of order, both are of order m by m, and U is of the same size as that of A. We shall show this in an example in the next few slides. Let us now learn the algorithm of PA equal to LU decomposition. We first write the given matrix A in the manner IA is equal to IA. So this is the way I write the matrix in this manner. Here I is an identity matrix which is of the same order as that of A. And if we know that A is a square matrix of order M, if A is an M by M matrix, then I is also an identity matrix of order M. But if A is a rectangular matrix, the given matrix is rectangular, then to here the I will be an identity matrix of order M. Meaning to say here that M here denotes the number of rows. So if I have a matrix of order 3 by 4, then I3 would be considered rather than I4. If it is a 3 by 3, it's automatically, which is a square, I am taking a 3 by 3 matrix. But if I have the number of rows to be 3 and columns to be 4, then I would be considering the identity matrix of order 3. And then I proceed. That's my first step. So when I write it as IA equal to IA, my aim is now to reduce the left hand side I to the permutation matrix P, the right hand side I to a lower triangular matrix, and the right hand side A to an upper triangular matrix, keeping this A as it is. So this is my goal, to reduce it into that particular format. So let's see what will be my next step now. So as we recall, row exchanges are permitted here because that will be taken care by the permutation matrix. In the process of reducing the right hand side A to an upper triangular matrix, I can perform row exchanges. So now let me see in the second step what I write. So perform row operations to reduce A, which is on the right hand side. So I wrote IA is equal to, let me write down here, IA is equal to IA. I am reducing this A into an upper triangular matrix. Now in order to reduce it, this may require swapping of rows. And whenever there is a requirement of swapping of rows, say for example, I am swapping the first row with the second row. In that case, then the swapping has to be done in two places. Kindly note, the swapping of the corresponding rows must be done in A, which is the right hand side A, and the left hand side I. So the swapping has to be done in both the places. So when you know that in the process of reducing the matrix A on the right side to an upper triangular matrix, if we are swapping the first and the second rows, that swapping has to be done on the left hand side I matrix and the right hand side A matrix. More so, the right hand side I that I have, I must perform the swap only to that part of the identity matrix which lies below the main diagonal. So if I am swapping first and the second row, I can swap those elements in the identity matrix in the right hand side, but only to that part of the identity matrix which lies below the main diagonal. I'll explain this in the example. It will be more clear at that time. So this would be the procedure when you are swapping. The remaining procedure which we followed in LU decomposition in my previous video which I explained, that will continue to be the same. So the only change here is whenever there is a swapping of rows that is done, please note that that swapping has to be done on in the right hand side matrix A, the left hand side matrix I, and only to that part of the right hand side I which lies below the main diagonal. So what we mean by that, we shall see it in the example in my next slide. So this will be the procedure. So once I reduce it, when I'm swapping, these are the conditions. Otherwise, when I use the other row operations, like I multiply a row by a non-zero value and I change Ri as Ri plus or minus k times Rj, these are the ones which we have already used in the LU decomposition. That will continue to be the same. What is changing or what is new here is only the swapping of the rows, and this is the step 2 takes up the main step where we have to know which are the matrices where we have to swap the rows. So remember, right hand side A, left hand side I, and right hand side I will be only that part of the two rows which lie below the diagonal. So let's apply this in our next slide, certain examples. Let me take up the first example where we decompose a square matrix. I have considered a 4 by 4 matrix in this manner. And if you note here that the first element itself is 0, so that cannot be done directly and therefore it requires exchange of rows. So let me first write down, as the working rule said, we shall rewrite it as IA equal to IA. So I write the matrix in this manner. If you look at this, it is I, A on the left side, again I on the right side along with the matrix given to me, which is A. So because I have the first element to be 0 and I should not continue it, I need to have a non-zero pivot value. So I will exchange it with the second row. So I will exchange the first and the second rows, and so I write the operation as R1 is swapped with R2. So where are we going to use this swapping? As we discussed in the previous slide, it should be done on the right hand side matrix A and the left hand side matrix I. So this matrix, what's happening, this row is going to become here and this row is going to come here. Same way here, this second row is going to occupy the first row. The first row is going to occupy the second row. And I also said for the right hand side I, we have to look at those values of R1 and R2 which lie below the diagonal. So if you see in this, this is the diagonal. And there is no element of R1 here and we have only a 0 here in this position. There is no element where we can swap. So this I, there is no operation that is to be performed. So we will keep it as it is. So this right hand side I is kept as it is. The first two rows in the left hand side I and the right hand side A is swapped. So let's see how the new matrix will look like. This is it. So here the second row comes up. First row goes to the second. The I here, there is no change. As I said, below the diagonal I said. And below the diagonal, when you look at this, below the this is the diagonal. Below the diagonal, there is no R1 term. There is only one R2 term, which is a 0. So I don't have to swap. I said below the diagonal, not along the diagonal. So this will be untouched and will be kept as it is. Now what happens? Now if you see there, the first term is -1. I need to make it 1. So because I am using an operation, I multiply the whole row by -1. So I write the operation as R1 is changed to -1 R1, in which case, which we saw in LU decomposition, this -1 takes up the position in place of 1 here. So in place of 1 on the right hand side I, it will become -1. There is no other change anywhere else. So P, the permutation matrix P continues to be, but the one which is kept as I continues to be as it is. On the left side, only change is this. So this minus 1 is now occupying this position, and the first row of the right hand side a is multiplied by minus 1, so it becomes 1 1 minus 1 and minus 2. Now this position is 1 is already there, this is already 0, this is already 0. We said below the first, along the first column, below the pivot element, I want all zeros, so this position has to be changed as 0. Operation obviously will be R3 is changed to R3 minus 2R1. So what is happening, this 2 will occupy this position, and the remaining terms will follow the operation. Let's see how it's getting transformed. So you're getting this 2 here, so 2 is coming to this position, and by using the operation, the third row minus 2 times the first row, then you get a new third row in this manner. Now coming back to the next diagonal element, you see it's again a 0. Then there's a new next diagonal element is 0. First column is done. 1 followed by zeros is done. Coming to the next column, again we are having a 0 there. So which I have to swap. I can swap with either R3, which is minus 1 there, or I can swap R2 with R4. But since I have a plus 1, I would like to swap it with R4. But you could also swap it with R3 and you would get another decomposition. So I am swapping here R2 with R4. So what is happening here? Now in the left hand side I, again swapping should be done in this left hand side I and the right hand side A. So let's see what's happening. The second row. The second row now will occupy the fourth row, and the fourth row is going to go back to the second row. So the left hand side will become 0 1 0 0 0 0 0 1 0 0 1 0 1 0 0 0. So I will be that. And now coming to this, the second row is going to be swapped with the fourth row in A. That's a very common thing to do. Now look at what we said for the right hand side I. Now right hand side, what did we say? Now leave out the diagonal. Below the diagonal are these elements. Now which two rows are swapping? The second row and the fourth row. Is there going to be any change? What is the element in the second row? 0. What is the element in the fourth row? 0. So do we have to swap them? Not necessary, because they are anyway only zeros. There is no change required. So we will leave that matrix as it is, and therefore the new matrix becomes this. So you see the fourth row here is becoming the second row, and the second row is now becoming the fourth row. So that's what it's happening. And here again, the second row is becoming the fourth row. So here this is changing and this is changing. And here we have not touched, it is kept as it is. There's no change in the right hand side I. Now coming back, so now we have got this particular pivot to be 1. I want to make this element 0, so I perform R3 to be R3 plus R2, and that again I am only, this minus 1 is going to jump up to this position, because that's the change that I want. There is no change in the left hand side I matrix. So the left hand side I matrix remains the same, no change. And this minus 1 is occupying this position. Likewise, R3, the row 3 is changing based on the operation of adding it with R2. Now you see, the first column is done. The second column is also done. Now what should we do? We have to change this minus 2. So we divide it by minus 2 so that I make the third diagonal element also 1. I'll show that in my next slide. So as I told you, the next diagonal has to be touched, and that was minus 2. So I made it 1 by dividing it by minus 2. So that minus 2 position comes here. Now I still have minus 1. Now you look at this. Below the third diagonal element, I have minus 1. How do I get rid of it? So I add it with 1 in the third row. So that's the operation. R4 is R4 plus R3. Thereby, this minus 1 occupies this position without changing the permutation, left hand side permutation matrix. And you see, only again I have minus 1 occupying this position, and the last element that I get diagonal is minus 5. My aim was to derive or reduce that matrix A into an upper triangular matrix having all once along the diagonal. That's actually called the Kraut's reduction. So we ensure that the right hand side values, the right hand side matrix A has ones along the diagonal and it's upper triangular. So I divide it by -5 and thereby rewrite -5 here. And when I do that, what happens? You see, -5 comes here. It occupies this position and this becomes 1, and all the diagonal elements that I have here is 1. So now this is becoming a lower triangular. This is becoming an upper triangular, as you can see it very clearly. So you have permutation. This I is becoming P here. So we have now reduced it to the form PA is equal to LU. So we have followed the similar structure as we did in LU, except for one case where it is whenever there is a swap, what are the changes to be done? So now the PA equal to LU decomposition is done with the matrix P on the left side and with the matrices L and U on the right hand side. Now we can also verify whether we have done it correctly. Now we said here PA is equal to PA is equal to LU. So suppose I take the inverse or the transpose on the left side and push P to the right side, we learned that P is a matrix, an orthogonal matrix. So whether you take inverse or transpose, it's equal to P. So A is equal to PLU. If you multiply the three matrices, you should get back A, and I think that can be verified by multiplication. So it can be verified that A is equal to PLU. So I hope that this problem is clear. This involves two stages where row exchanges are done. And when row exchanges were done, we took care to see that the right hand side matrix A and the left hand side matrix I, the swapping is done, and the swapping is done only on the right side of I, only to that part where the elements lie below the diagonal. The necessity was not there in this problem because the values that I had were zeros, and swapping of zeros makes no meaning. And maybe we would see another problem where you can show I'll show you the effect of how this I can be transformed. So in a similar manner, let's take up a rectangular problem matrix now and ensure and see how can it be written in the form as PA equal to LU. I hope this problem is clear. Yeah, let us now look at the second example where I have considered a 3 by 4 rectangular matrix. So let's proceed with in a similar manner. You see here that I have written it as IA equal to IA. I have written I on the left side, I on the right side, A along on the right side, and we have automatically 1 here, so there is no need of any change. So that 1 is automatically even there. So there is no need of any change there. But I need to make these two positions 0. So I will write it as R2 is changed to R2 minus 2R1. So that this position will become 0. And R3 plus R1 will make this position 0. Automatically, these two elements on the right side I will change. Left side there is no change because we are not doing any swapping. And if you see, this 2 and -1 are occupy these positions. These two become zeros. And now these are the values that change based on the operations. We have now the second diagonal element is 0 and that requires a swap. Now we have only 3 rows. So we are swapping now R2 and R3. So what is now happening? Let's carefully watch. So we have now R2 and R3 that is swapped. So that swapping, where all should it take place? It should take place here in the left side I, in the right side A, and to that part of I on the right side which is below the diagonal. This is my diagonal. R2 and R3 are to be changed. Now you see here they are both non-zero, so it makes sense. So these two values also I should swap. Now the second row and the third row should change. Fully it should change on the left side I, right side A, and these two elements which lie below the diagonal, the right side I. So you see what happens now. So let me erase this so that yes, now we can check it out. Now you see here what have we done? The second row and third row are swapped. So I get the third row here and second row here, as you can see in these two. And now, as I said, in this right side I, the second, these are the two elements that lie below the diagonal, and second and the third rows are swapped. So minus 1 will occupy the second position, 2 will occupy the third position. So this is where that the condition that I said, that I, in the right side I, only that part of I which lies below the diagonal should be swapped. And here, of course, 0, 5, minus 1, 1, which is the third row, now becomes the second row. 0, 0, 6, 5, which was the second row, becomes the third row. So now what is the pivot element that we have here? It is 5, and now I require to make it 1. So I divide by 5, and so that 5 will occupy this position here. So let's see what's happening now. You see 5 is occupying this position, and the remaining values are similarly simplified. Now what do I have to do? I've made, this is a 3 by 4. So you have a rectangular matrix. So it's only 3 diagonal elements. So the third diagonal element here is 6. So I divided by 6 to make it 1. And let's see what's happening again. So that 6th position is occupied here. This becomes 1. The remaining values are all non-zero. So we have reduced it into a lower triangular, upper triangular, and we have a permutation matrix because we have only one row exchange being done. So this is your permutation matrix. This is your lower triangular and upper triangular matrix. So the decomposition is done, and in a similar manner it can be verified that A is equal to PLU. So I hope these two examples have given you an idea as to how to take care of the row exchanges that we need to perform in order to reduce the matrix A into an upper triangular matrix. Now, keeping this as a base, let us now take up a problem of solving a system of equations using the PA equal to LU decomposition. Having learned the decomposition technique of PA equal to LU, let us apply it in solving a system of equations. Let's consider a system of 3 equations and 3 unknowns as it is shown here. We first write any given system in a matrix form as AX equal to B, where A represents the coefficient matrix, X represents the coefficient of unknowns, and B represents the constant matrix as we have seen here. So A is 1, 1, 1, 2, 2, 3, 1, 2, 3. X represents the vector of unknowns, and of course the constants, which is 4, 1, minus 1. Now we have the matrix or the decomposition that we need to look at is PA equal to LU. Let's elaborate this before we start working on it. So we know PA equal to LU is the decomposition we need to make. Let us post multiply by X. So X is the vector that we know. So we post multiply by X on both sides. Then we rearrange them, write LUX on the left side for our convenience sake. And then place the brackets. PA into X can be written as P into AX. So that this AX is nothing but B. So I substitute that here, so that I get L into UX is equal to PB. So you have now and a PB on the right side, which is again a new matrix. Let me now take Y to be equal to UX, so that LY is equal to PB, where Y is equal to UX, and Y is a new variable having the components Y1, Y2 and Y3. It's a 3 by 3 matrix which I have considered here. So naturally, when now I have here PA equal to LU, I have two sets of equations. LY is equal to PB and Y is equal to UX. Now X is my actual unknown, but since I know P and B, which because I will be declaring it in decomposed form, let me first find Y. Then I use that Y here, and then I find out the values of X. Just like we did in LU decomposition, but there we did not have P there. It was Ly equal to B. Here it is Ly equal to PB. That's the only difference between the two. So now let us first decompose the matrix A in LPA equal to LU form, and then start off by simplifying the first set, which is Ly equal to PB, and the second one, which is Y equal to UX. Let's see that in our next slide. Let us first find the PA equal to LU decomposition for the given matrix. So we start with IA equal to IA and write down the matrix I into A equal to I into the given matrix, the coefficient matrix. It's already 1 here, so I need to make this 2 and 1 to be 0. So the operations are R2, which is R2 minus 2R1, and R3 is R3 minus R1. They occupy these positions in I. So the new matrix now becomes 2, 1. This has already become 0, 0. But you see that the second pivot element is becoming 0. So we'll have to interchange the two rows. So the second row and the third row are interchanged. And this interchange takes place in I on the left, A on the right. And now you see 2 and 1. 2 and 1 are the elements that lie. So these also have to be swapped because they are below the diagonal and they occupy the second and the third row positions. So I am changing that. So this 2, 1 becomes 1, 2 here. And the second and the third rows get swapped. So automatically you are writing PA equal to L into U form because all the diagonal elements in the upper diagonal are 1. So this transformation or decomposition is done. Now we have to start with the first system that we have to solve. It is Ly equal to Pb. L is this matrix. So I've written that. Y is y1, y2, y3. P is the permutation matrix, which is the final permutation one. And B, which is our constant matrix. So when we multiply it, we get such a system. So we use it as nothing but here the lower triangular matrix, and therefore we use the forward substitution. So 1 into y1 is equal to 4. 1 into y1 plus 1 into y2 is minus 1. 2y1 plus y3 equal to 1. And on solving, I get y1 is 4, y2 is minus 5, y3 is minus 7. Having got the values of y, now we need to solve ux equal to y. What is u? The upper triangular matrix which we have framed. X are the required unknowns and y are the values which we have just now got. And using the back substitution, I get the values of x1, x2, x3 in this manner. So this is how the system of equations is simplified using the PA equal to LU decomposition in a similar manner, just like how we did LU, but by taking care of row exchanges. So dear friends, I hope that these two videos which I brought out in LU decomposition, the concepts are clearly put and you have an idea of how this decomposition works, maybe some examples that you could take. And if you have any doubts, or you can please post it in the comment section. To the best I can, I would be able to answer. And hoping to see you in some other videos. This was a request from some of the subscribers, and so I prepared and presented it. In case you require any other topics, videos in it, please feel free to comment in the box so that I could work on it and present the video. Thank you. God bless. We'll have a wonderful New Year 2023. The clock has just struck 12 o'clock on January 1, 2023. God bless you all. Take care.